Chapter 4 is about variability. With variability, what we're going to look at is understanding our data not based on a measure of central tendency. So the most common measure of central tendency is the mean. Let's take a look at these two sets of quiz scores. We got Class A, let's call them the Tuesday class, where we got a full range of scores on a quiz. Anything from a 0 to a 10, a couple of 4s and 5s, almost there. And then we got a 7, did okay. We got a 10, they aced it. Would that class be the same as my Thursday class, let's say? They get a Class B, 0, 0, 1. So I got 3 people that virtually know nothing. And then 9, 10, and 10. I got 3 people that have mastered it. Class A, good spread, a little bit here or there. Wish I had more people up in the 7s. Class B, you either got it all or got none of it. Are these two same classes? Like performance-wise? No, right? Nowhere near. But if we were to take a measure of central tendency like the mean, do some quick math. 0 plus 4 is 4, plus another 4 is 8, 8 plus 5 is 13, plus 7 is 20, plus 10 is 30. The mean is the number, the sum divided by the number of observations. 30 divided by 1, 2, 3, 4, 5, 6. 30 divided by 6. It's 5. Do the same thing for group B. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 9 is 10. 10 plus 10 is 20. 20 plus 10 is 30. 30 divided by 6. 5 again. So I've got 2 sets of numbers. Their averages, their means, are both 5. But looking at the distribution of the scores, they look nothing alike. So the measure of central tendency is a good way to take a data set and describe modality, so what is the most frequent score, and the symmetry of the distribution. So we can look at it and say, okay, let's look at our group B. What does the symmetry of B look like? I've got 3 that are over here on this edge, and I've got 3 that are over here. My symmetry is sort of like a 2-hump or a bimodal symmetry. Looking at distribution A, my highest point is going to be 4, but then I'm going to quickly go flat. And I'm going to be skewed. I'm positively skewed. So these two distributions are not alike at all. But if you just use a measure of central tendency, it's going to look very similar because they both have the same mean. So what we're going to add to our understanding is what we call measures of variability, to understand how the distribution of scores are different from each other. So if the mean can be a measure of how similar the scores are, not similar, that's probably the best example of a score. A measure of variability is going to tell us how different they are from each other. Okay. We need these measures of variability, because when we look at these distributions, they all have the same mean, median, and mode. We've got a set of 3 distributions here. They're all unimodal. They all have one mode. But the scores themselves for our shortest distribution, very wide. Our tallest distribution, very narrow. Those scores are going to be all together. Again, the mean for all of these is the same. The exact same for these three distributions, A, B, and C. But looking at the data, here's a way to say, okay, what are we truly just getting from the mean? Or the median or the mode in these three distributions? That's what I've told you. But to describe the distribution, what does the mean, the median, and the mode give us? Right, if we're going to draw it. It may be symmetry, because if the mean, the median, and the mode are all the same, then the distribution is symmetrical. Lorenz? Does it give us the range? It does not give us the range. The mean, the median, the mode give us a starting point. Okay, so that's all it says. It says, listen, start your distribution here. If we know that the mean, the median, and the mode are all the same, we also know that the distribution is going to be shaped how? Symmetrically. Okay, we know that. But what we're missing is the shape. Tall and skinny, short and stout, comfortably curvy in the middle. We don't know that. And that's what variability gives us. It gives us proportion. Is that, we want to think about it that way? Right? It gives us a sense of, not the shape, because we know the distribution is going to be bell-shaped, but it gives us a sense of the proportions of it, the relative ratio between height and width. Does that make sense to you? It makes sense to me, but I want to make sure it makes sense to you. Just one person nodding. Come on, Doug, help me out. Yeah? Get the shape thing? Proportion? All right. I've told you before that this normal distribution is kind of a magical thing. Take a look at this weight rack. Do you notice anything about, perhaps, which weight do you think gets used the most? Where's the pin usually go? You think the 60-pound is used a lot? Why? Okay, because the rubbing of the paint off the plate is pretty big, right? Which plates probably used the least? $150? You think 150 is used the least? Yeah, these two are probably used the least, right? Down here and up here. Why? Because they're the two extremes. So you're telling me you're not going to lift a 15-pound weight? Right. And so this has the least paint used. Okay. Why aren't you going to lift a 15-pound weight? It's not going to do much. You know what weighs 15 pounds? My fat cat. Daisy weighs 15 pounds. I don't need to go to the gym to lift Daisy. Right. So it's going to be used the least. But take a look at this. Turn your head sideways a bit. What you should see, I love that you guys are actually doing it. Thank you so much for doing that. I love it. Power. All right. If you turn your head sideways, because I'm not going to flip the picture sideways. I'm going to make you guys look like idiots. Turn your head sideways, squint your eyes, get in tune with your mathematical self. What should you see? Gregory, what do you see there?
I don't have the mathematical self.
Squint your eyes extra hard. What do you guys see? get? What kind of a distribution? Give me the N word. Right? See, I can just turn my screen. You guys can't do that. All right. Once we hit about 40 pounds, we start to see a little bit of a hump to our curve. Remember, you're turning your head sideways, so you're going to see this as a curve. You see this as a curve? All right, I got lots of head nods. You guys see this as a curve. I'm not crazy. Look at that. In the wild, an example of what a normal curve looks like. If we were to collect data on people, what should our average lifting weight be? About 60 pounds. Now, looking at the shape of this distribution, do you think we have a lot of variety or just a little bit of variety? We have variety. It exists. I'm not going to tell you if there's a lot of it or not a lot of it. You got some? There's more plates being used than plates not being used because nobody's using 15 or 20. And what's funny is that 25 is probably just the rubbing from the people using the 20. Like all the pins that I've used usually like point down. Right? So there's lots of people out there lifting 20 pounds. Okay. So it looks like we're getting a lot of use in the 45 to 70 range. And then it kind of, a little bit of a break here at 80. Not a lot of people doing 80. If you're doing 70, you might as well just be starting at 90. But then nobody really does over 100. Not a lot. Not a lot of reps. That's the other thing too. This isn't just measuring the weight that people select. It's actually a measurement of reps because the number of times that it goes up and down. So we're getting a lot of reps in this 45 to, let's be generous, say 90 range. And we may get people trying to do 100 pounds, but they're not going to do 90 reps of 100 pounds. Whereas you might do 90 reps, that's 3 by 30, of say 35 or 40 pounds. Okay. Make sense? Good. So how can we measure this variability? Well, we got a few different ways. The simplest one is called the range. Now, it has to be of our observed data. The two ends of the distribution, the range is the highest score minus the lowest score. And you would just say our variable x ranges from 10 to 90 for a range of 80 points. Whenever I report test scores to a class, I like to give them the range. Why? Yeah, so they know where they are sort of in the class. If you got a 70 on the test, what does the fact that the highest score was an 86 tell you? That your 70 is not so bad, right? If you, let's see, if you got a test and our high score is 86 and our low score is 12, what's that tell you? I really hope I'm not the 12, right? It's like, man, my 70 sucks, but at least it's not a 12. Okay? So it helps you sort of place yourself. And then what really you need to know is the average, right? That way you can say you were either above average or below average. So the range, whenever I report test scores, I like to give people the range because I want to give them a sense of how far did we actually go. Yes, you could have gotten 100, but functionally nobody really got out of 86. That was a good test. It was a nice, strong, hard test. You all are like, that's an awful test. Like somebody should be able to get like 100 on it. So that's the range. We've seen this one before. Thinking of a curve, what does the range tell us about the shape of our curve? Maybe, right? It gives us an idea of where our low point and our high point are. So maybe a little bit about the width, just a little tiny bit about the width. Because if I say that the highest score on a test is 86, that's about where the distribution ends. Right? See how this curve here ends right around this point, but these curves keep going. Maybe, just a little bit. A little bit of information helps us understand what our curve would look like. Going back to our weights example, if I know that the lowest point is a 15 and somebody actually used the 15, like there's a scratch there, I promise. But then you go down and like these suckers down here, 130, 140, 150, they haven't moved. I don't even think they work. Nobody's touched these ones. We got some scratching on 120 because of 110. That appears to be like the real limit if we're collecting actual data, like snooping at people as they're lifting at the gym. We would say our range is probably from 20 to 120. That's a 100-pound range. Good thing about the range, really easy to compute. Like you guys have this whole subtraction of a smaller number from a bigger number thing down pat. That's first grade math. Good thing about the range is it's easy. And the only other strength is it gives us something. It kind of gives us our point of our curves where the tails end. Gives us a little bit of something. The mean gives us the middle point, the tails give us, or the range gives us the beginning and the end. But there's some problems. Why it's not really a good statistic. It's really only based on 2 scores. So the range is based upon, for our test example, the smartest kid and the not smartest kid. Okay, the dumbest kid. I'll say it. I'll be mean. That's it. And when you're in a room full of 40 people, that's not very comforting. So it's affected by extreme scores. Those outliers are going to affect the range. Because if you have 2 outliers, a really, really smart person and a really, really dumb person, that doesn't describe the other 38 people in the room. So let's make it a little bit better. There's something called the interquartile range. The interquartile range is the middle 50% of the scores. Interquartile range. The goal is to take off the lowest 25% and the highest 25% to give us just what's in the middle, and therefore we're not as worried about outliers. That's pretty. So what am I going to do? I'm going to find the 2 points of my curve. what two scores give me 25% on the top end, 25% on the bottom end, and my interquartile range is the 50% in the middle. My two outliers not going to bother that. And we like to think of things in half. So half of the scores are between this range and this range. Now, what if your test score is above the interquartile range? How do you feel about yourself? Pretty good. Why? Because you're in the top 25%, right? I'm in the top 25. That makes me feel good. I tell you that the lowest score is a 12, but you only got a 30. You're like, ooh, not so bad. But if the interquartile range lower bound is 18, yay, right? I'm not in the bottom 25. I'm doing a little bit better. I'm like right here maybe. There's 10 people in the class worse than I am. All right, interquartile range. Strength, we've reduced the influence of outliers. Yes. Weakness, we're still ignoring half the scores. I can't get over this. Like, you're creating a statistic to represent a group, a set of variable, a set of data, and we're just going to ignore half of them. We're literally taking that data and ignoring it. We're not even using it at all. Might not even have, why bother collecting it? Just throw out the A's and the F's. Or in this situation, the B's and C pluses. Can't tell you guys how important it is to want to preserve all your data. You worked hard to collect that data. You want to make sure that as much of it as possible gets into your analysis. And when you generate a statistic that ignores half of it, you're not being very efficient. So here we go. This is the one. This is it. The one we need. It's called variance. Variance is a measure of variability. Of course. We're going to use a statistic based on all of the scores in the distribution. Which now you're thinking, oh man, it's going to be a lot of math. Because I'm going to have to do something to every single score. Every data point is going to be used. We denote variance by S squared. That's what that 2 up there is for. One summer when I was going to math camp, I was crossing the border, and I said, they asked you where you're going. I said, going to Ann Arbor, going to math camp. And the guy's like, A squared, huh? I had no idea what the hell he was talking about. I'm like, no, Ann Arbor. He's like, yeah, A squared. Are you sure you're going to math camp? I'm like, huh? Ann Arbor, A is A. I'm like, oh, I get it. Can I go now? Don't joke with customs. Just don't shoot me. All right. So that's my squared joke. I didn't get it. He's like, yeah, have fun. Good luck with that. The basis for variance is to look at the scores, so each individual data point, and see how far away they are from the mean. it differs or deviates from the mean. So mean is an important part of our distribution because the mean centers our distribution. The high point and the low point from the range tell us about where those tails are. But knowing where the bulk of the observations are from the mean is going to tell us whether or not we have a tall curve or a short curve. If our standard if our variance is small, then there's not a lot of variation from the mean. What is our curve going to look like? It's going to be skinny and tall, right? Because we're not getting away from the mean. Make sense? I just need one light bulb to go off. Make sense? All right, got some vigorous head nodding. If I have a large variation, which means there's lots of distance from the mean, what's my curve going to look like? Okay, that was a shitty curve, but you get the point. Right? Because a lot of the bulk, a lot of the weight, a lot of the observations in our data are going to be far away from the mean. Okay, I'm going to show you an equation. It's not that hard. Looks a little scary because there's a squiggly mark in there, but don't be scared. Yes? Sure. So in terms of the width, right, from high to low, that's set by our range. But we got to pack all of our data points in between those 2 points. That just tells us the beginning and the end. The shape of it in the middle depends upon whether there's variation from the mean. Those 2 data points, the beginning and the end, they're just the beginning and the end. Doesn't really tell us anything about the shape of the curve, just really the length of the curve. Low variation means most of our data is going to be in the middle. And that's why I make it tall, right? Because I got to put all of that bulk in the middle. But lots of variation, I got to take that area, that bulk, and it fits between my beginning and my end. Better? Okay. So here's the equation. Not that hard. Not that hard at all. The squiggly thing I thought was there isn't even there yet. That's the next one. So S squared, variation, is equal to the sum of the difference from the mean squared divided by n minus 1. So let's take this and break it into parts. What's the first thing we can do, order of operations wise? Parentheses. So we got to know what x is. We have to know what x bar is. And then we need to subtract them. No, don't end the show. Make sense? Your book has a way in which they can take this and actually plug in sum of x divided by n. I don't want you to worry about that. I want you to focus on the simpler formulas. So what do we do next? We've got this part here in the middle. And you can't see me, you put my finger on the screen. We got that part in the middle. What do we do now? What do we do next? We square it. take whatever number is in here and we square it. All right, then what do we do? No. We've got this. What's next? We got to sum every one of those together. So this one plus this one plus this one. Right? Doug, you with me? Promise? Okay, Doug's still with us. That'll give us the numerator. I'm summing up all of these x minus x bar squareds. I'm going to add them up, put a total at the bottom of the column, and then I'm done with that numerator. N minus 1, what's n? Number of observations, minus 1. Why minus 1? A little bit of theory here. So we're generating a statistic. This variance is a statistic. And whenever you do this, sometimes you want to take out one observation, and it's called the degree of freedom. We'll get to it like around chapter 8, but this is the first time we see that idea, where we're just sort of pulling out an observation saying, you know, let's just be careful. Now what happens by making the numerator, the denominator smaller? What does that end up doing to our number? Makes the number smaller or bigger? So we're saying that there's potentially, we're reporting a number that has more variance than maybe it actually exists. And that's a good thing. We're being cautious. You just got to trust me on this. File it away, I'll come back to it later, and you'll be like, oh, that's why n minus 1. Okay. N minus 1, that's simple subtraction, and then we've just got a very, very simple fraction, and then ta-da! That's s squared. Okay? There's a reason we have to square it. So we saw it was the sum of the differences squared. Well, look what happens if you don't square them. Here's an example from your book. We've got x bar, you do the subtraction. What's going to be the sum of x minus x bar if we don't square it? Minus 1, minus 2, that's minus 3, minus 4, minus 5. So we got a total of minus 5. And then we add to it 0 plus 1 is 1, plus 1 is 2, plus 3 is plus 5, minus 5 plus 5 is 0. Shit. What happens when you have a 0 squared? Doesn't matter. Zeros are bad. All right? We'd have a 0 in the numerator. Bad. It doesn't make any sense. That's why we square these things. 1 squared is, 2 squared is, 1 squared is 1, 2 squared is 4, 1, 9. No matter what we do, when we square something, we take away the negatives. And so we can still capture the distance from the mean. Got me? Right. And we can measure how much it goes away from the mean, because it's always going to be positive. A little bigger than before, right? Because any number is bigger than 0. But at least we have a measure of how far away you are from the mean that doesn't always cancel each other out. Gregory, got it? Okay. Got to make sure you understand why Sometimes we do things. Because I told you the variance is the distance from the mean. And this is the distance from the mean. But to get one number to represent this data set, I'd always end up with 0. So that's why it's s squared in the notation. Well, yeah. You always square it. Take every number and you square it. The best part about it is I don't have to pay attention when I square a number whether it's positive or negative, because it always ends up being positive. One of those stupid math rules from 7th grade math that didn't make any sense then. So you're telling me I got -4 and I'm going to multiply it by -4 and I got 2 negatives and somehow I'm going to end up with a positive? Yes. Why? I'm not explaining it to you. That was your 7th grade math teacher's responsibility. I'm just saying it is. It has to do with the number line. -4, -4 times, keeps going at 16. Just does. So that's the great sort of mystery of math that's going to bail us out here. Because whenever you're dealing with your entire data set and you're using the mean, it's always going to cancel each other out. So that's why sometimes you got to square things. And that's why it's s squared as your variance. Hey, look, that's what I just did. All right. You don't believe me? Son of a bitch. So basically, what did they do here? They did the columns like we did. They squared it. And I just wrote this in on the side, right? 1, 4, 1, 4, 1, 9. And then they used that, the sum of this, 1 plus 4 is 5, plus 1 is 6, plus 4 is 10, plus 1 is 11, plus 9 is 20. So the sum of these is 20. In this example, they had 1, 2, 3, 4, 5, 6, 7, 8, 9. And is 9, take 1 away because just trust me. N is the number of observations in your data set. How many data points you have. How many numbers you're dealing with. How many scores. So the variance of this data is 2.5. Somebody put in the margins x bar equals 3, s squared equals 2.5. I need one person to do it. Doug's got it. All right. That's nice and everything, but we don't like things in squares because it just creeps us out. So we've taken that variance and we've decided to use another version of variance more frequently. This is called standard deviation. And again, you've all learned this before in middle school. Because let's just say the variance is the average squared deviation from a score. Average squared deviation from a score. That doesn't work for me because I don't think of things in squares. So if we just take the square root of it, ta-da, the standard deviation becomes the average deviation. Okay? Yep. So I just built this thing called s squared. And that is the average squared distance from the mean. Because remember I had to square it to get that average distance? It doesn't work for me. I don't think of things in squares. I think of them in terms of distance. So if I take a square root of that, I'd get that squared word away. Listen, I didn't come up with this. I'm just trying to sell it. It's a little shady. And I could have fixed it if I used absolute values, but if, man, you guys don't like exponents and square roots, you really hate absolute values. Because it's functionally the same thing. When you square something and then take the square root of it, all you've done is just taken the absolute value. See how much middle school math is just coming back to you? Right? 13-year-old self's like, I'm never going to use this. Yeah, you will. Someday. It's the exact same equation with a square root on it. Little tip for using your iPhone to do calculations, turn it sideways. You get more buttons, including the square root button. That's about the only time in this class you'll need to turn your phone sideways. So if this is the deviation, this is the average, right? And you do this, and this is the squared. Well, by taking the square root, we're getting rid of the squared, and all we're left with is the average deviation from the mean. This number will always be what? Yeah! Oh, warm and fuzzies. This number will always be positive. Why? Because negatives and squares don't mix. Okay, so this is always going to be a positive number. Hallelujah. When we do our whole sample versus population thing, which I covered last week, so you got to watch the video. When we're doing a sample, we tend to use regular, good old-fashioned English, whatever the right name for this is, letters, A through Z. When we do populations, we tend to use lowercase Greek. Population, it just means everything ever. Sample is what we commonly work with, a selection from the population. And we talked about this once before, right? You guys are a sample of coastal students. You're not every coastal student. Like, there's more than just the 20-something students here at Coastal. Okay. So if mean, M mean is mu, standard deviation is sigma. That's a lowercase sigma. It's a little o with the arm. Not a hat, because if I say hat, you're going to think this hat. Because to me, that's a hat. X bar is a hat. Or there's also a little hat in math sometimes with the up arrow. There you go. It's got a ball, well, visor. That's a little O with a visor on. All right, that's the standard deviation. So what would the population variance be? Yeah, the little O with a ball cap squared. Okay. Standard deviation makes the most sense to me. The average distance from the mean. I can get that. Because if we're drawing out a distribution, here's my mean, average distance. That distance could be forwards or backwards. Doesn't matter because the curve is symmetrical. And that's why that everything's positive doesn't matter. Okay, so if my sigma is 3, that means the average distance from the mean is either positive or negative 3. It goes in both directions. You find yourself doing this. Whenever you have a curve, you find yourself putting these little barriers up on both sides. Because it goes in both directions. Okay. So variability, any measure of variability, is an attempt to quantify the degrees in which our data scores are different from each other. We got some really poor ones. That whole range thing doesn't really work so well. The better ones, the one that makes the most sense, variance or standard deviation. Those are the ones we like. We like them the most because they do what? Why do we like variance and standard deviation the most? Uses all of our data, right? That's why we like the mean the most, because the mean uses all of our data. We really, really like this. Here's this funny thing, though. Remember how I told you about this magical curve? Variance is kind of magical, too. When you're a mathematician and you're looking for patterns, it's great when you find one and you find that they have pretty much universal application. So in a normal distribution, our measure of variance, standard deviation, because we just got S. It turns out, oh, it's a good looking curve, that about 68% of our data is going to fall within one standard deviation from the mean. So again, you got to just sort of get into this practice. I'm going to draw a line. It's going to be plus 1 and minus 1 standard deviation. %68 of it's going to be there. Here's the really good thing, really, really cool thing for us. About 95% of our data is going to fall between positive and negative 2 standard deviations. You look at test after test after freakish thing in nature, reps in a gym, shoe sizes, batting average of baseball players, miles per gallon of cars. Whatever the data set is, if you know what the standard deviation is and you know the mean, you got a pretty good shot at being able to sketch this thing out and understanding what the shape of it looks like. This is known as the empirical rule. That term empirical, we use that a lot in social science. In fact, if I were to describe myself, I would describe myself as an empiricist. Because the type of work that I do relies on empirical observation. And what is empirical observation? Data. It's all data. I'm an empiricist, which means I make conclusions based upon data. Now that's the opposite of what? Awesome. I'm going to give you guys 2-week breaks every time. What does a normative person make decisions based upon? Whatever the hell they think things should be, right? They might have ideals, they might have what they think are rules of logic, right? But I'm an empiricist. I believe in data. And our empirical rule has found this neat little quirk about the standard deviation. Plus 1 standard deviation, 68%. That's a good solid number. We have a term for that. That's a preponderance. The preponderance of evidence. And 95%. That's a number we love in the social sciences. $95 is like magic time. We love this concept of 95%. And we default to this term, statistically significant. And that's when you got something. When we have an article and you've done a table and you find something that's outside of this 95%, put little stars next to it. We're like, hey, look at the pretty thing over here. This is nice. You should look at this. Sometimes we put 3 stars next to it. But just to get 1 star, that's about 95%. That's what we like. So this is a magical number. We're going to remember this idea of the empirical rule at 95%. When you get 3 standard deviations, well then it's like almost all. 99.7% of our observations will fall within 3 plus and minus 3 standard deviations. That's like all of them. Some people will use this as a shortcut to find a true outlier, something that is way, way, way afield. So because of this great coincidence that we have with the empirical rule, we can start really understanding the shape of our distribution. I'm going to show you a little applet. This applet will draw for us a normal distribution. Math speak, up top here, let me make it bigger. Math speak, normal distribution X is a variable that's tilde, little squiggly line, distributed n for normally. N stands for normal distribution. There's 2 parameters, there's 2 statistics that tell us the shape of any normal distribution. Mu, which is our mean, and sigma, which is our standard deviation. So as we change mu and sigma, 2.5, the shape of our distribution changes. All right, so if I want to make this distribution really, really skinny, what should I do? Yeah, son of a bitch. Look what they did. They kept my shape of the curve the same. What did they change? There it is at 0.5. Here it is at 2.5. Yeah, all they did was change the numbers at the bottom. What kind of demonstration of the normal curve is this? Jerks. All right. Let's give it an actual number. Our normal, oh, sorry, that's not the number we want. We want 5.5. Okay, so empirical rule says that plus or minus 1 standard deviation should give us 65% in the middle. So here's our distribution again. I got a mean of 3, standard deviation of 2.5. I added 1 standard deviation to it, and it put that mark down. This is the spot right here is 5.5. And then it told me how much area of the curve is left in the tail. So 100 minus 68 is what? Thank you. So why doesn't this say 32? Why isn't it 0.32? Not a trick question. Because why? Yeah, because it's symmetrical, right? Because this is only showing me the positive side. It's not going to work, but I'll try it. 3 minus 2.5 is 0.5. Yeah, it doesn't like that. What the hell? See, now it's giving me 84, which tells me that there's 16 left over here. Oops, this is the one I wanted. There we go. So there's my other 16% right there. The empirical rule was 2 times. So if I go out 8, what should this number be? If I go out 2 times, 1 standard deviation, 2 standard deviations, what number should be left in the tails? Somebody with conviction. Back to the empirical rule. Look down in your notebooks. You just wrote this down. Empirical rule. 2 standard deviations. How much does 2 standard deviations cover? 95%. So how much is going to be left in that one tail? How much? Thank you, Mary Kate. Found your voice. We've got, so far we got 97%. If I switch this around, a little over 2%. Ta-da! Empirical rule. We love this thing. This is going to be really important for us. This idea of the empirical rule. Now that we have a measure of central tendency and we have an idea of variation, we're going to start thinking about our data in distribution form. So we're going to start thinking about our whole big data set. And we're going to start to focus in on values of that data set. This is what you do when you get that information about your test scores. Oh, it's a sweet-ass curve. All right. Who in here has heard of the LSAT? What's the LSAT? Law School Admissions Test. The LSAT, in my department, as the pre-law advisor, is the test that students freak out about the most. What do you know about the LSAT? It's really hard, and it's a lot of logic games. So the law school test isn't anything about law. It's interesting. The LSAT, as an exam, is a standardized test. What does that mean? It means they make your test score fit a standard distribution, which is the normal curve. It sets a minimum and a maximum score of 120 to 180. You know how many times they give the LSAT? Yeah. They give it 4 times a year. Each test is different. That's not fair, right? When I give a test in a class, everybody gets the same test, right? Why? Why can't I give Mary Kate, you have like 3 names. You got to give me a break. All right? Why isn't it not fair that I give Mary Kate a different test than I give Anna? I'm not using a different measure. It's a test. How do you know I'm not equaling measuring those two? Like hers just has different numbers for one mean question and hers has different numbers for a different mean question. It's not the same. See, that's the thing that bothers everybody, right? Pardon me. Right? If I don't get the exact same thing as the other person gets, it's not fair. Well, sorry, Abby, but you're 8 and John's 4, so I do have to differentiate between what you two get. Stupid kids. You all act the same way. Well, what if my LSAT's different than their LSAT? I took the LSAT in December, they took it in April. Yep, you did. But the answer to that question and that complaint is, that's okay. We're going to standardize the scores. You take the LSAT in April, the average number of correct answers on the April LSAT is 80. Dr. Wood, what the hell? You've got numbers 120 to 180, but you put 80 in the middle. That doesn't work. You're right. Because what the LSAT people do is they figure out which algorithm, which equation to apply to that 80 to get it to translate to a different number. $150. Now, why would you want to take 150 from an 80? Because what is 150 in terms of LSAT scores? Our new average. That's what it means to standardize a test. It's to take your raw score, like the number of questions you get right on a test, and to standardize it to fit the normal curve. Which is why any one of you idiots that ever goes to a professor and says, will you curve this test? You have no idea what the hell you're talking about. Because this is what we mean by curving a test. Making the raw scores fit a predetermined distribution. That's your LSAT. That's your SAT. That's your GRE. That's any standardized test you've ever taken, down to the Iowa test that you all took as kindergartners. Standardized test. It's not standardized because everybody takes the same damn test. It's standardized in the score because the scores are designed to fit a distribution. You've been lied to your whole entire lives. That's the neat thing about this distribution is we can put multiple x-axes on this curve. This can be a distribution of raw scores translated to a distribution of reported scores. Next class, I'm going to add a new one. It's called a z-score. And it's the same exact thing as an LSAT score with different numbers. Okay? Cool. See y'all next time.